Weinberg. So we are discussing evolution and populations. Now, Weinberg is used during population genetics. Population genetics is the study in genes in a population to see if the evolution occurs, and then to predict if a population is evolving. We talked about Hardy-Weinberg equations. It's also called Hardy-Weinberg principle. So these are used to calculate and predict allele frequencies and genotypic frequencies in a population. So we learned already these equations, Hardy-Weinberg equations. Hardy-Weinberg is the name of the two sciences, Hardy and Weinberg, that came up with the Hardy-Weinberg principle to see if evolution was occurring in a population. So these are going to predict allele frequencies and genotypic frequencies Now, Hardy-Weinberg said, with his equations, that unless evolution is occurring, these are going to remain constant. So, allele frequencies and genotypic frequencies will remain constant from generation to generation, unless evolution is occurring. That is how we know if evolution is going to occur. I'm going to highlight this in red. The frequencies will remain constant from generation to generation. So these two equations that you need to understand. Write these in red. P plus Q equals 1. That is one equation. P squared plus 2PQ plus Q squared equals 1. These numbers, ones, will remain constant from generation to generation. That makes this easy when talking about the other types of ways to figure out frequencies. Just remember, Hardy-Weinberg says everything is always constant. Now, let's look at these equations. You need to understand what all of your P's and Q's mean. So, P, Q, P squared, 2PQ, and Q squared. So So we're doing allele frequencies and genotypic frequencies. P is always going to be your dominant allele. Q is always going to be your recessive allele. So, when we did allele frequencies, we did dominant versus recessive allele. Okay, so when you say P squared, you have two P's, two dominant P's. This is going to be your homozygous dominant genotype. 2PQ is going to be heterozygous because it's got a P and a Q, one dominant and one recessive. So if you have two recessive alleles, Q squared, then that is obviously going to be homozygous recessive genotype. So by looking at this information, which equation is used to predict allele frequencies? Which equation is used to figure out genotypic frequencies? That should be pretty obvious. But we know in Hardy-Weinberg that these frequencies are always going to equal 1 and will remain constant from generation to generation. Any deviations from these numbers indicate that evolution in the population is going to occur. That's what makes these equations super easy to use. So, deviations of observed frequencies, because they should always equal 1, using the Hardy-Weinberg equation, indicates evolution in a population has occurred. They should always remain constant. Any deviations from 1 means that you have evolution. So when we use Hardy-Weinberg equations, there's 5 assumptions that we use. I'm just going to get a new piece of paper. There's 5 assumptions that we use. Remember, they must remain constant. These remain constant. Any deviation means evolution that occurs. So you can only use Hardy-Weinberg equations with 5 assumptions about a population. First thing is they will always remain constant if the population size is large enough. If you have a small population, everyone's going to eventually start to look like each other. Think about if a population size was just you and your family and like maybe 2 other families, and that's all you had to be in your population. Eventually you would all start to look alike. So the population has to be large enough so that you can overcome any random events. The second thing is obviously your choice of mates has to be random. So if we took that same population and they said you could only have children with a certain family, then you wouldn't have a random mate. So eventually the population would start to look alike. So we should say that no evolution is going to occur in a population if you choose random mates. The third thing is mutation does not occur. You don't turn purple. Most of the time, mutation will occur. It takes years and years and years and years and years and years for you to ever see it. But the population size is so large that even if you have a mutation, it'll eventually go away. The fourth thing says, if we're looking at a population, individuals can't leave, because then that's going to change. Migrate. They don't migrate in and out of the population. The only way it's going to remain constant is if people aren't leaving. The next thing is there are no selection pressures. I have to explain this one. When we say that there are no selection pressures, that means factors such as temperature or predation, like no one's like coming and hunting you down. Meaning that if everybody who had a dimple on their chin was being hunted down, if anyone who has a dimple on your chin is being hunted down, you're being predated, then basically there's no selection pressures happening. But if everyone in your population with a dimple got hunted down, then eventually no one would have a dimple on their chin. So selective reproduction, you would start to choose your mate based on if they had a dimple. You would be like, I'm not going to mate with you or my child's going to get killed. So selection pressure can also be temperature that makes people die in a certain area. This would be more like if we were talking about polar bears in the North and South Pole. But no selection pressures. No one's hunting you down. It's going to always remain constant. So the population has to be large enough. Your mating has to be random to always get the same numbers, not mutating an entire population. People are not leaving and entering a population. Now, obviously, Hardy-Weinberg can't be used in most places, but if they go to maybe Antarctica, they can use Hardy-Weinberg equations because everything is, pretty natural. But you couldn't use this in Big Spring, Texas because our population is probably large enough, or mates are random. Mutations probably don't occur, but individuals leave, and especially college students, they come in and out of our population. We don't really have any selection pressures, so These are going to be based on 5 assumptions, that the reason why they would be constant. Now, there's a lot of different ways to do Hardy-Weinberg. We're going to keep this very simple. So, you're always going to be given either P, Q, P squared, 2PQ, or Q squared. So you should definitely know what everything in the equation means. So you're going to have practice in your worksheet, and I'm going to give an example of each. So these are going to be practice. So that you can go through and do yours and make sure that you're doing it right. So practice using Hardy-Weinberg. These are going to be different. Your tests are going to have these, so you might want to understand these. So if this is the information that's given, you're going to use your Hardy-Weinberg. So you have to know P plus Q is equal to 1, P squared plus 2PQ plus Q squared is equal to 1. Know what each one of these stand for. So, if the recessive allele is 0.2, what is the frequency of the dominant allele? So the first thing that you need to do is figure out what's given and then what's being asked. So using our chart, the recessive allele is Q. That's what's given to you. So Q is equal to 0.2. Now, the question is asking what is the dominant allele, so I want to know P. Literally says what's the frequency of the dominant allele. That's what I want to know about. This is how you have to read these questions. So P is equal to question mark. So you look at your equations, P plus Q is equal to 1. So since it's always equal to 1, you say P, what plus what equals 10, which is 0.10 is 0.8. And then you're done with that one. That one's an easy example. All right, so second example. So you can do that in reverse. If the recessive, now let's do dominant. If the dominant allele is 0.9, what is the frequency of the homozygous recessive genotype? So you need to figure out which part of the equation I'm asking for and which part is given. The frequency of the homozygous recessive genotype. The dominant allele is what's given. So you always go back to this. So the dominant allele is P. So P is equal to 0.9. What I want to know about is homozygous recessive, Q squared. Now, don't let this throw you off. The easiest thing to do is to figure out Q using the PQ equation. So if P is equal to 9, Q is equal to what plus what equals 10 or 1, it would be 0.1. So Q squared would be your homozygous recessive genotype. So 0.1 times 0.1, you have to move your decimal over. Q squared is equal to 0.01. That would be your answer. So I'm going to tell you, anytime you're given a Q squared, a P squared, or a 2PQ, always figure out your P's and your Q's. So say, mind your P's and Q's. I don't know if y'all have ever heard that saying before. Let's give some more examples. C. If the dominant allele is 0.3, what is the frequency of homozygous dominant genotype? So this one's a little easier. You just have to figure out what I'm asking. I want to know, here's my question mark. This is what I'm asking for. So you go back to your original thing. The dominant allele is P, so P is what's given. P is equal to 0.3. Homozygous dominant genotype, P squared. So I literally write P squared. Now, since P is given to you, 3 times 3 is 9. But you have to move your decimal over. 0.09. 0.3 times 0.3 is P squared, and you're done with that one. That one's an easy one. So if you're ever given something, figure out P and Q first if needed. All right, now let's go a little more in detail. If you're homozygous recessive genotype is 0.36, what is the frequency of the recessive allele? This one's easy too, if you know what they're asking. So the question is saying, what is the recessive allele? But you've got to go through what's given. Homozygous recessive genotype. Homozygous recessive genotype. Oh, this is a mess up. This should be Q squared. I'm glad I caught that. So Q squared is equal to 0.36, but the question is asking, what is Q? Well, what times what is 36? The answer is 6. So Q is equal to 0.6. That one is easy. You're done with that one. You're keeping up with what the question is asking and knowing your equations. All right, the next one. If the homozygous dominant genotype is 0.81, what is the recessive allele frequency? What is the question asking? What is the recessive allele frequency? So what do I want to know? PQ, P squared, 2PQ, Q squared. What's given? Homozygous dominant genotype. Homozygous dominant genotype is P squared. So P squared is equal to 0.81. What am I asking for? The recessive allele frequency. So recessive allele is Q. This is what I want. So this is another equation where figure out your P's and Q's. So what I would do is take this one and figure out your P. So P is equal to 0.9, because 9 times 9 is 81. Again, if P is 9, then that means Q is equal to 0.1. 1 times 1. There you go. The recessive allele frequency. I already figured it out. If I asked what was the homozygous recessive genotype frequency, you would say 1 times 1 is 0.01. You're done. Don't make it hard. Always figure out your P's and Q's. So here's another example. You should write these out and see how I'm doing these. If the homozygous recessive genotype is 0.49. What is the heterozygous frequency? Oh, now we're starting to throw in 2. So again, what is being asked of you? What is the heterozygous frequency and what's given? So let's see. Homozygous recessive genotype is Q squared. Q squared is equal to 0.49. And we want to know about heterozygous frequency, which is 2PQ. Man, find your P's and Q's first. Mind your P's and Q's. So first thing I would do is figure out Q. Q squared, what times what, is 49. Q is equal to 0.7. Then, once I figure out Q, because P plus Q equals 1, I'm going to figure out my P. P is equal to 0.3. Then all I have to do is my 2PQ. So, you literally are going to say PQ, let's put a parentheses around it. So you say 0.7 times 0.3 is 0.21 times 2. So what I did, I put a parentheses on here. 0.7 times 0.3 is 0.42. Then I take that 0.42 times 2. Oh, yeah. 0.84. I think that something is wrong. Hold on. Oh, it's 0.21. 0.21 times 2 is 0.42. That would be your answer. Now, if you want to see if you're right, remember that P squared plus 2PQ plus Q squared should always equal 1. So if you know Q squared is equal to 0.49 and 2PQ is equal to 0.42, you already have P. 3 times 3, P squared is equal to 0.09. Add these up and you can equal 1, and then you can see if your answer is right. So this is your answer. And it looks pretty right, 1.01. So again, always figure out your P's and Q's and then work to the bigger question. All right, the next example. If the homozygous dominant genotype is 0.64, what is the homozygous recessive genotype? Know what your P's and Q's mean? Know your equations. Know what I'm giving you. So the homozygous dominant genotype is P squared is equal to 0.64. Homozygous recessive genotype, I want to know Q squared, question mark. Figure out your P. P is going to be 8.8. 8 times 8, 64. The next thing is I figure out Q. Q is equal to 0.2. 0.2 times 0.2. Q squared is equal to 0.04. Remember to move your decimal over because that will mess you up. So those are examples. Mind your P's and Q's. Know what each of the equations stand for so that you can do these Hardy-Weinberg equations.